Okay, let's formalize this approach a little bit more. So we're going to pick an endpoint B for the interval x0, b0, and remember that this x0 comes from the initial condition. Where we had y of x0 equals y0. So that x0 is our initial condition, that's where we start, and then we pick an endpoint B on which we want the approximation of the solution. Then what we do is we divide the interval x0 comma b into n equal subintervals, x0 to x1 and then x1 to x2 and so forth until we have xn minus 1 to xn, where x sub n equals b. And we can then define a step size h as follows. So we're going to subtract x0 from b. That gives us the length of that interval, and then we divide it by n. What that means is that each of these little intervals now has length h. And we have n of them. So another way of thinking where x1 is, we can think of x1 as x0 plus h. x2 is x1 plus h, or if we start at x0, it's x0 plus 2 times h. And in general, when we get to x sub I, we get that that is equal to x0 plus I times h. So that I plays a role here. And that's the first part of our Euler method. Right, so this is the first important formula. Okay, now how do we find the y values? To find the value of y1, we can use the point slope formula for a line through the point x0, y0 with slope m. Right, this is our equation of the tangent line. Now, in our case, the slope was given by our function f at x0, y0. That's our initial condition, and we start there. Dy dx is equal to that, and that's the slope of the tangent line. Now, for this line to figure out what y1 is, we need to plug in for x, x1. So what we get then is that y1 equals the slope, right? That is f of x naught comma y naught, and then times x1 minus x naught, and then plus y naught. But x1 minus x naught, that's the distance between these 2 points, that's just h. So we can rewrite this as y1 equals h times f of x naught y naught plus y naught. Now, in general, you can show that when you do this again for y2, we still have the h here, because if we do the same for y2, we get x2 minus x1, and that's your h. You would then plug in f of x1, y1 here, and then you would put y1 here. So in general, we can show the following, that yi plus 1 is equal to y sub I plus h times f of xi comma yi. And that's the second part of Euler's formula. So the next y, you can find it from the previous y by going h units to the right and then multiply that by the slope of that tangent line, and that will give you the change in y. Okay, so let's do an example. We'll start out relatively simple. We have the initial value problem dy dx equals 1 over 2 times the square root of x with an initial condition of y1 equals 1. We want to find the Euler approximation of the solution on the interval 1, 5 with n equals 1 and n equals 2 steps. So let's start with n equals 1. So for n equals 1, what does h become? H is b minus x naught over n, and the endpoint for which we want the solution is 5, and then the initial value is 1, so that's 5 minus 1, and then we have one step, so h equals 4. That's not very realistic. Normally the h is a very small value, but this is just for illustrative purposes. So now we can use the formula over here to list all the xy's, or sorry, all the xi's. So I'm going to list all xi's. And we start off with x naught equals 1, and then we only have one other xi, x1 equals 5, right? And you see here that we're adding the step size there. That's the plus 4. So we now already have all our x values. So now the next step that we need to take is we need to calculate our yi's. And so the formula that we're going to use here is this one over here. So calculate the yi's. And so y naught is given, right? And that's this one here. That is our x naught. And then y1 equals, according to our formula here, that's the previous y plus h. And let's just write that out. H times f of x naught comma y naught. And now let's plug in what we know. Y naught equals 1. H is 4. And then f of x naught y naught, That's f of 1 comma 1. And our function here is given by 1 over 2 square root of x. So let's write that on the side. So this is 1 plus 4 times 1 over 2 times square root of 1. And that's the x value that we fill in here. So f of x comma y equals 1 over 2 times square root of x. And add that all up, and the final answer is 3. And so if we then write down the conclusion, we can say the approximation passes through one comma 1, our original point, x naught, y naught, and then x1, y1 will be 5 comma 3. And if you'd like to, you could just connect those 2 points up with a straight line as the solution. So this is x naught, y naught, and this is x1, y1. Okay, so let's do the same thing for n equals 2. Let's calculate our step size. That's b minus x naught over n, and that's 2. Well, I guess I can just write n for now. And then we get 5 minus 1 over 2. And we see that our step size h is 2. Okay, now list all xi's. We now have 3. We have x naught, x1, and x2. X naught is 1. Then we add h to that, we get 3. And then we add h to that again, and we end up in 5. Right, so we have plus 2 and then plus 2. Okay, and now we can calculate our yi's. So calculate we start off with y naught being equal to 1, y1 equals y naught plus h times f of x naught, y naught. And so that is 1 plus, and h is 2, so it's 2 times f of 1 comma 1. And that is 1 plus 2 times 1 over 2 square root of 1. It's a half plus 1, so y1 equals 2. Now I'll draw a box around it so that we can keep track of that, because when we do y2, we need to refer back to y1. So let's do that on the side here. So we have y2 equals the previous y1, plus h times f of x1, y1, and y1, that's equal to 2. H is equal to 2 as well. And now we're plugging in x1. We get that from here. So that's 3. And then y1, we get that from here. We get 2. Oops. So that's 2 plus 2 times 1 over 2 times square root of 3. Now notice that that 2 doesn't matter at all, because f of xy does not depend on y. And we get that that is 2 plus 1 over square root of 3, which is approximately equal to 2.577. And our final answer then, we can say that the approximation passes through one comma 1, 3 comma 2, and then finally 5 comma 2.577.